All right, so good afternoon students. The last class we had just begun with the small signal analysis of FETs. We'll just very quickly go through the recap. Okay, so we discussed about the course, the chapter contents, and regarding the JFET small signal model, we discussed on the expression of the transconductance factor, okay, or the parameter which is called GM, okay, graphically as well as mathematically. So GM is the transconductance factor which is given as delta of ID upon delta of VGS. Okay, so please note that the term delta means that there is a small change. Okay, so what is the small change with respect to the current ID whenever there is a small change with respect to the gate to source voltage? Okay, so that particular change is being it's being taken up in the form of the transconductance factor GM. Okay, so graphically it is just the slope, okay, slope of the vertical axis upon the horizontal axis, right? So yes, so graphically we had seen how to obtain the transconductance parameter. First of all, you will be getting the Q point, and depending upon the value of the delta, okay, if delta is larger, then you will be getting a less accurate value of GM. If delta value is made extremely small, then the GM value will be extremely accurate. Okay, so it is just a slope, right? Okay, GM value can also be found out mathematically using the Shockley's expression. Well, slope is nothing but if you take the limits, okay, tending to 0, then it is just the derivative. So it is the derivative of drain current with respect to gate to source voltage at a particular fixed Q point. Okay, so when you just differentiate the drain current with respect to VGS after a series of 2 to 3 steps, you will arrive at a very simple expression which is 2 IDSS upon Vp multiplied by 1 minus VGS upon Vp. So that's the expression for the transconductance parameter found out mathematically. At VGS equal to 0 volts, we'll be getting maximum transconductance, okay, which is 2 IDSS upon magnitude of Vp. Okay, so when we substitute it, it is just GM equal to GM naught 1 minus VGS upon Vp. Okay, so that's the expression which we get. We had solved a problem graphically as well as using the Shockley's expression mathematically, and we just found that both the things both the methods will yield almost same values. Okay, fine. With respect to the plots, okay, the graph of conductance versus VGS, you will observe that there is a linear dependence. However, the point is when VGS is equal to 0, the transconductance will be maximum. Okay, maximum. When VGS is equal to Vp, the transconductance will be minimum. Okay. Further, the effect of ID, drain current, on the transconductance parameter, since there is a square root dependence, when we plot it, we'll just observe that GM varies quadratically. Okay, so you can just observe the graph, right? It's not a linear one, it's a quadratic variation, right? Okay, with respect to the drain current ID. And then coming to the expression for input impedance for a JFET. Input impedance for a JFET ideally is infinite, okay, but practically it is in mega ohms. Okay, practically it's in mega ohms, right? Then coming to the output impedance expression, output impedance for a JFET is denoted by the symbol small r with a subscript small d, RD, which is equal to 1 upon GOS. Okay, which is also equal to 1 upon YOS. So it is in terms of admittance parameter. Okay, admittance. So O stands for whenever the source is open. Okay, fine. So going to the output characteristics, you can obtain the output impedance RD, which is equal to delta VDS upon delta ID. Okay, so the procedure is again the same. Just notice the Q point on the drain characteristics, and depending upon the value of the delta. Okay, see, what do we mean by delta? See, delta VDS is the change in drain to source voltage. Okay, I'll just write it as variation. See, we are focusing on AC analysis. Okay, so there is obviously a variation in the applied voltage, right? So whenever VDS is varied, in what way does ID vary? Okay, so that change is being taken up with respect to this ratio as RD. All right. So now let us try to understand the JFET AC equivalent model. Okay. So what do we have here? When we just go through this particular equivalent circuit, we'll just observe that gate terminal is present, drain is present, and then the source is common. So we obviously have the source terminal also. But what about these terms? VGS, okay, and what about this GM, VGS, and then RD? Okay, why are we representing these particular parameters in such a circuit, and why do we call this as JFET's AC equivalent model? Okay, let's try to understand it. But for that, we'll have to focus on the constructional aspect of a n-channel JFET. Okay, so we are comfortable with this particular structure of a JFET, right? Okay, if this is n-channel, okay, then these two regions will be of P type. Okay, so they are gate, right, and they are shorted together so that there is a single gate, and this terminal it is drain. Okay, and let this be the other end, let it be the source. Okay, so that's the source, that's a drain. Fine. Now the point is, when VGS is 0, there will be maximum current for a n-channel MOSFET. As the drain voltage increases, more and more current flows, and after certain stage, there will be pinch off, and after pinch off the current gets saturated. So if you just focus on the drain characteristics, so this is ID versus VDS at some fixed value of VGS. So let us just assume that VGS is 0 itself. Okay, now as VDS increases, the current through the JFET increases linearly, right? Okay, so this is a linear variation. So whenever there is a linear variation, there will obviously be a resistance offered by the particular channel. Okay, so that particular resistance, okay, see, there is obviously a change in the resistance offered. It's not a fixed resistance. The resistance continuously keeps on changing. Now since we are trying to understand this particular chapter with respect to AC, right? Okay, it is AC analysis, so it's not VDS, there is a small change in VDS. Okay, similarly there will be a change in IDS. Okay, delta change. So this region offers some resistance, which is being represented by the symbol RD. Okay, so that is why we are placing a resistance here. Now after pinch off stage, okay, so this is pinch off VP. After pinch off, that means when both the depletion regions tend to join each other, okay, they just appear as if they are joining each other. Okay, so this stage is called pinch off VP. After pinch off, the current just saturates. Okay, so when the current saturates, we mean that there is a constant current source, it is not changing. So after pinch off, we are in this stage, in this path. Okay, so before pinch off, okay, the current flows across this path. After pinch off, it is just a constant current source that takes over. Okay, fine. So that's the current IDS. Now the point is, let us just differentiate between the normal voltages and the DC voltages and the AC voltages. See, VGS, we usually denoted gate to source voltage by this particular symbol, right? However, if there is a small change in VGS, okay, then we represent it by VGS, small gs. Similarly, small change in the drain current, IDS, is represented as capital I subscript small d small s. Okay, so because of that, we represent GM as the variation in the drain current with respect to variation in the gate to source voltage, which is IDS upon VGS. Okay, so please remember these terminologies and also the parameters. Okay, fine. Now the point is, at the output side, okay, either the current flows through this path or through the output impedance path. Okay, so this will be in the linear portion and this will be in the saturation portion. Okay, so what about the input? Anyhow it is a voltage controlled one, voltage controlled, and we know that the current, gate current, is 0, right? So obviously then the variation, the small variation in the gate current should also be 0, okay, because the main IG is itself 0. Okay, so due to that, we are just keeping it as a open space here. Okay, we are not joining it, right, because the impedance offered is infinite, right, because the current is 0, so impedance is, whenever I say impedance, it is input impedance at the input side. Input impedance offered is infinite, okay, but practically also it's pretty large and is usually in mega ohms. Okay, so because of that, we are just keeping it as open, right? So that's the AC equivalent of a N channel JFET. So with this concept, let us move forward and very quickly try to solve a problem. It's a simple substitution based problem. Given are the values of GFS. GFS is nothing but transconductance GM itself. Okay, and further GOS is RD, the output impedance is 1 upon GOS, right? So with these two values, you are supposed to sketch the FET AC equivalent model. So it's a simple substitution problem. Find the GM value and find RD value and then just substitute it in place of the circuit, right? Okay, so with this, let us move forward and try to understand. Yes, so again we have arrived at fixed bias configuration, right? What is the need to study this fixed bias configuration again when we had already studied it in our previous chapter? The point is, in a previous chapter we studied all the three configurations with respect to DC analysis, right? Okay, so just to say, DC analysis of fixed bias, and we also did it for self bias and voltage divider bias, right? And voltage divider biasing configurations. Okay, for during the DC analysis of these particular biasing configurations, there were some common steps, right? And the common steps were that we used to assume, right, that the capacitive reactance was infinite. Why? Because capacitive reactance is given as 1 upon 2 pi fc, and the DC signal, the frequency of DC is 0, so 1 upon 0 will be infinite. Okay, so due to that, we consider the capacitors to be open circuit, right? C1 and C2 were considered to be open circuits, and because of which we ignored input voltage and the output voltage. So both were ignored and then removed out of the core part, right? So that was the common step we followed in DC analysis of these particular configurations. But what about AC analysis? In the AC analysis also, we have some series of steps which are supposed to be followed commonly, but these steps are exactly the opposite of DC analysis step. Okay, so what is the first step? Okay, let us just go through it. The first step says, note that both the capacitors have the short circuit equivalent because the reactance Xc equal to 1 upon 2 pi Fc is sufficiently small compared to other impedance levels of the network. So what does it state? Again, if you go through the expression, Xc equal to 1 upon 2 pi Fc. For AC analysis, AC in the sense the signal is continuously varying with respect to time. Okay, so obviously the frequency is not 0 here, it is a large value. So that gives 1 upon some large value gives Xc value a small thing, okay, a small value, and this Xc value is sufficiently small when compared to the other impedance levels of the network. So what about the other impedance level, which means the Rg, okay, and the drain resistance. So when compared to these two impedance, the capacitive reactance is extremely small. So because of which we assume that C1 and C2 behave as short circuits. So this is exactly the opposite that we used to do it in the case of AC analysis. So for the DC analysis. So in AC analysis, assume the capacitors as short circuits. Further, what about the DC supplies, VGG and VDD? Okay, so VGG is here and VDD is over here. So these two voltages should also be replaced by short circuits. So just write DC supplies should also be replaced by short circuits. So these two are the most important steps in AC analysis, right? So what did we do now? So far we have seen how to represent a JFET by its corresponding AC equivalent model, and just now we went through 2 points, okay, point number 1 and point number 2 for AC analysis. Okay, so can we just add these two things and get a complete AC equivalent model for a fixed bias configuration? Yes. Okay, so that can be done, and we'll be doing the same thing in the following slide. Okay, so what are we trying to do here now? We are trying to obtain the AC equivalent circuit for a fixed bias configuration. Fixed bias configuration. Okay, so please pay attention so that because this explanation remains the same for other configurations also. Okay, the steps are same and the concept is also similar. Okay, so what should we do initially? Let us first draw the AC equivalent of JFET, okay, which we have already seen. So how do we do that? That's the gate terminal, okay, and source is common and it is being held at the ground potential. Okay, so let us give it a minus symbol, and plus minus, the input impedance is infinite, so it is just open circuit, and VGS is the input voltage which actually controls the entire device. Then at the output side, so that's the drain end which is held at positive potential with respect to the source. What do we have here, by the way? We have a voltage controlled source, right? So that's a voltage controlled source, and which is being represented by GM VGS. Then in across or parallel to it, we have the output impedance denoted by the symbol RD. Okay, so that is the AC equivalent of JFET. Now to this particular JFET, we will have to add the additional components, right, which means the capacitor C1, C2, the DC supplies, all the things. Okay, so what should we do? First of all, the capacitor. Okay, we know that the capacitor should be replaced by a short circuit, right? So I'll just write it. This is the capacitor C1 which is replaced by a short circuit. Then similarly, what do we have? We have the resistance RG which is in parallel. Okay, so resistor RG which is in parallel. Further, what do we have? We have a DC supply VGG. Okay, and we have seen that the for AC analysis, wherever there are DC supplies, replace them by short circuit. So I'll just replace it by a short circuit. Okay, and that is VGG. Okay, fine. So that's our input VI. Okay, so we are done with the input side. Now coming to the output side, what do we have at the output side? Again, at the output side we have a capacitor C2, so this has to be replaced by a short circuit C2, and then parallel we have a drain resistor which is represented by the symbol RD. Okay, capital RD, and then again we have a DC supply which is to be replaced by again a short circuit. Okay, that's it. So that is output V0. Okay, so I think we are done with the entire circuit. Okay, but just to clearly differentiate between the things, let me choose a different color so that I can very clearly represent, right? So which is the core JFET AC equivalent model? Okay, the one which is being highlighted now, okay, with blue dots. Okay, so that is the JFET AC equivalent, right? So to this JFET AC equivalent, we are trying to add the capacitors, the resistors, and the fixed DC supplies by their respective AC equivalents. Okay, so which is, so C1 is here and C2 is here, it's again a short circuit, and DC supply VGG and the DC supply VDD. Okay, so they are being represented here, but generally in your textbooks, okay, these the capacitors and the fixed DC supplies which are replaced by the short circuits, okay, and these are not explicitly mentioned, so you can just ignore henceforth all these things. Okay, fine. So that's your AC equivalent fixed bias configuration circuit. Now what about the expressions? Okay, the input as well as output expression. If I want the input expression for this entire AC equivalent circuit in terms of input impedance. Okay, so that's the input impedance, and the output impedance appears here, the output impedance. Okay, see, for input impedance, I'll have to look through the input, the portion of the input circuit ignoring the effect of the output. Similarly, for the output, I'll have to ignore the effect of input and then just only concentrate on the output portion. So how do I represent input impedance? Zi, input impedance, Zi. Okay, so what is the resistance here? It is only Rg. So the input impedance is Rg. Okay, you can just check here. It is just capital Rg. Okay, very simple. Then coming to the output impedance, Z0. Output impedance Z0. Now, if I just look at the output side, I'll be getting two resistors. Okay, one is the output resistor of the JFET itself, which is the small Rd, and another one is the external resistance Rd, and both of them are in parallel, right? So I'll have to write small Rd, which is in parallel to capital Rd. That is the output impedance offered. Okay, now usually, since these two things are in parallel, I just forgot to mention current here. Okay, so that is the current I ds, small ds. Okay, so that's the current which is flowing through the circuit. Now, as a thumb rule, okay, suppose if a current IDS is flowing and we have two paths. Okay, one is small Rd path and the second resistance path is large Rd path. Okay, usually this small Rd, okay, it is the output impedance of the JFET, right? It is usually much larger when compared to the external resistor Rd. Okay, so we usually say, your textbook says, usually if small Rd, okay, which is usually greater than 10 times of capital Rd, then okay, in which path does the current flow? Okay, the current always follows the least resistance path, right? So it usually flows to this path. In such a case, if both of them are comparable, then the current splits equally. However, if one resistance is much higher when compared to the other resistor, then the current usually flows through the lesser or the least resistance path. Then the output impedance can be given as almost equal to capital Rd. Okay, this expression holds good only when small Rd is much greater than at least 10 times of capital Rd, or else, okay, so that's the expression for input impedance and that's the expression for the output impedance. Okay, then moving forward, let us again focus on the output portion. Okay, how can I express the output voltage? See, voltage is nothing but the product of current and the resistance. Okay, so it is IDS multiplied by the resistance offered at the output side. At the output side, the resistance offered is Rd parallel to capital Rd. Okay, now how can I represent IDS? See, IDS is the current which is flowing, and this I can represent it as, it's actually the current source, right? Gm multiplied by VGS, extremely important. Okay, this parameter, right? And multiplied by Rd parallel to capital Rd. Now how can I represent VGS, by the way? What is VGS? VGS is nothing but the voltage across gate to source terminal, and that is nothing but the input voltage Vi. So I can just replace it as Vi, right, multiplied by Rd parallel to capital Rd. So this is V0. Okay, now if I take the ratio of V0 upon Vi, what is it? What does output voltage upon input voltage give me? It gives me the gain, and since it is a ratio of voltages, it is voltage gain, AV. So the voltage gain AV equal to V0 upon Vi, which is nothing but Gm multiplied by Rd parallel with capital RD. Okay, so again, now if Rd is much greater, or at least 10 times of Rd, then I can simplify the voltage gain to be almost equal to Gm multiplied by capital RD. Now one small thing is missing here, that is the inclusion of negative symbol. Okay, for a n channel MOSFET, if you just look at the notation of the current source and that of this IDS, you will observe that we will have to include a negative sign here. Okay, minus. So everywhere I will have to include this minus symbol. Okay, fine. So that is the voltage gain expression for a fixed bias configuration by following the AC analysis. Okay, so hope this concept is clear for you. Okay, so what have we done? We have just understood how to represent a JFET by its AC equivalent model. Then taking that particular AC equivalent model, we have included it in the fixed bias configuration, and at the same time we have also replaced the corresponding AC equivalents of the capacitors and the fixed DC biases, and then all together clubbed it, combined it, and then obtained the complete AC equivalent model for a fixed bias configuration. Further, we have also obtained the corresponding expressions for the input impedance, output impedance, and the voltage gain. Okay, so AV stands for voltage gain. Just write it here. AV stands for the voltage gain. Okay, so let us look at the same aspects in terms of very clear diagrams. Okay, for a fixed bias configuration, AC analysis, you can just see that C1 is being replaced by a short circuit, C1, C2, and the DC supplies VGG and VDD. So all of them have been replaced by their corresponding short circuits. So when you do that, that is the simplified redrawn AC equivalent circuit. Okay, and then the input impedance Zi equal to Rg, Z0 equal to Rd parallel to small rd, and we have also looked at this particular condition. Okay, then the voltage gain expression. Right? Okay, so if you are pretty comfortable, if you thoroughly understand the basics of the AC equivalent JFET model and also the steps, okay, then you can easily derive the expressions for input, output impedance, and then the voltage gain. Right? So with those things, let us just focus on this particular example. You can try it at your home, but just what are the values that are being given here? VGS value is given, IDQ value is given, maximum drain to source saturation current value is given, and then the pinch off voltage is given. Then you have also been provided with the value of output admittance. What all things have been asked? To determine transconductance GM, output impedance RD of the JFET. Okay, these two things are associated with respect to only the JFETs, right? And these things are with respect to the complete circuit, complete fixed bias circuit. Okay, so we'll have to understand that, right? So what is the first step? The first step is to find out GM naught. gm not equal to 2 IDSS upon Vp, both the values have been given so that you can find out its value. Then subsequently find out the value of gm. Okay, then similarly RD value is 1 upon YOS, which is 25 kilo ohms, right? So that is for a JFET. Okay, then coming to the other things. Okay, you already know the expressions for input impedance, output impedance, and then the voltage gain. Okay, so just substitute the values and then find out the answers. Okay, all right. So that was all about the AC analysis of a fixed bias configuration. I'll just ask you that you apply the same steps, same principle, same concept, and then try to obtain the AC equivalent for a self bias and a voltage divider bias. Okay, and then let's just understand the same things in our next class. Okay, all right. So I think we will stop here and then continue on Monday. Okay, so any doubts, students? You can ask. Yes, any doubts, students? If there are any doubts, then just